laser parameter. So basically laser or whatever, if it is a nozzle also, what it will do, if it is, you are familiar with the FDM? So FDM also, you have a air gap. There is a, I don't know whether you are familiar with the FDM parameter. The quite similar parameter is the hand space. Air gap, in the sense same, the distance between the two nozzle parts. Say for example, this is your outer contour, right? Say for example, extrusion. So how it will be extruded, right? And similarly, your laser, what it will do? Laser will one path, and next pass. Maybe you can fill in several ways, right? You can fill in contour, or you can fill in raster, or you can have. Manjega cheppandi. Right. Lockdown.
More the space, more the porous.
Yeah, means if you have more space means like whatever you say.
More the porous.
Yeah. But it will quickly finish. The build time will be less. Yeah, then again we need to. Yeah, that's what it is.
Hello, professor.
Yeah, please.
No, if you don't less space, you can customization. But how do you feel about the maintenance of these equipments? This is the routine.
Maintenance.
How are you feeling? Maintenance, trans availability.
Yeah, this we are right now. We are under AMC, so we took 5 years AMC, so we are running 5th year. Almost we have AMC. So far, the 3D systems. It's a US company. So this is basically 3D systems.
Right.
Yeah, this is US company. It's a powder bed fusion. It's a PBF with the metal. It's a metal, and it's basically a laser energy source. And 100 watts is a laser power. Yeah, maximum 100 watts. And the scan speed, as I mentioned, 250 to 1500 is the range. Hat space is 30 to 120 micrometer. And the layer thickness right now we set as a 30 micron, but even it will go up to 50 micron. I mean 25 to 50 micron. That's a range. Yeah, basically these are the process parameters. As well as machine. Machine specifications we have here, so you can look. So if you see here, the machine specifications, build volume as already mentioned, 100 by 100 by 80.
It is here.
Yeah, you are asking about the specifications?
Yes, sir.
So it will support cobalt chrome, aluminum, titanium, 17.4 pH. All these are, even you can try our own material also, but this is the company recommended. Even we have the open parameters. We can develop our own material, and then accordingly we need to adjust the process parameters.
Sir, actually I have, in my research I have taken Inconel 25.
Okay, fine.
Is it possible to melt, whether I have to use DAD or SL?
Both it will work. Inconel, it's a proven.
Highest temperature.
Yeah, it will work for both. No, you are asking which one do you prefer, that's what you are asking. No, that depends, like you are looking for the resolution, more quality, powder bed is the better option, but if you are looking for faster and somewhat economical, DED may be economical if you compare with powder bed. Powder bed is
So in terms of fusion?
Fusion,
to make alloy.
Yeah, again I am telling, fusion you are going to manipulate with the energy density. Say, you can understand, with the 90 watts, you could able to melt the titanium. So what is the melting point of titanium? 1400. But you are using 90 watt, but you could be able to
calculate.
Yeah, that energy density. So energy density may be, power may be less, but what is the denominator? In the denominator you may be manipulating that, so you could able to get the energy density at that level, and you could able to melt the titanium. So titanium and your inconel also. Inconel also it will work. So all it's about, you can manipulate with the parameters.
So we can make alloy with this machine.
What kind
Yes,
of alloy?
yes.
Yeah. How no? What kind of alloy?
Like
Inconel, yeah, inconel.
nickel.
Yeah, nickel, any nickel based, but they are suggesting some grades like it is already they have given a preset of parameters. So if they are suggesting some inconel 718, so you have a
Yes, metal library.
Right.
You can select
Correct.
it. And it is automatically
Right.
according to the metal characteristics.
Yes, yes.
Yes.
So
Like titanium 6Al4.
yeah, titanium
That's
does
prefixed to that.
yeah parameters where so yeah, this is what professor I am talking about. So this is one of the accident case. He lost 5 teeth along with the bone support. But if you go with the traditional implants, so it will come 1-to-1. And that too, this patient doesn't have a bone support. So we cannot fix 5 screws. So then this is the indigenous design for this patient specific requirement. So because he had an accident and incidentally it was a asymmetric fracture. Because you are engineer, then you are comfortable if it is symmetric, then you can take the mirroring option.
Not the perpendicular.
Correct, yeah, it is a mirroring plane and then, but unfortunately it is an asymmetric fracture. Then the commercially available implants or won't work for this case. So then this is the indigenous design for him. So where during the surgery this has been built on this titanium 6-4. So and then it is fixed during
Only
this.
with the 2 screws.
Yeah, that's only 2 screws, and then on top of this 4 teeth it has been accommodated.
Actually, this.
Correct. Yeah. So means because there is no bone support, so then this is for him only. It's a personalized, customized implant, particular to this patient. But the commercially available implants, it won't work here. So
That is
that way.
Yeah.
And this is another case. This is a TMJ reconstruction. Patient had by birth. You have 2 joints. Yeah. So lower jaw, upper jaw. Yeah, as you said, like there will be a link. Yeah, joint. So that joint, by birth, she had a fusion of this joint like this. Yeah. But it should be free, then only responsible for the articulation of the jaw. What we have done is, but luckily one side okay. So then mirroring option has helped us to copy the same the dimensions from the survived to the defect one. So then using the software called Mimics, so we designed the implant and further we printed this, again it's a titanium, and then during the surgery it got fixed. So which you can see, this is during the surgery which it is fixed. So on the upper jaw there is a screws, and we have designed the guide also for the surgeon. So then for drilling the hole, so exactly this guide will support him where he has to fix the screw. So that template or a guide has helped them while drilling the hole. And we filed a US patent. It has been granted recently, US patent, on the TMJ reconstruction. So for oral maxillofacial surgeon, that is the toughest surgery. So we have a lot of nerves also here. There will be a lot of nerves associated in and around the joint. So that is another challenge. So normally that is the toughest surgery for a oral maxillofacial surgeon. But this technology will help these kind of complex geometry, the surgeries will make simplified, and the operating time has been reduced and the precision.
The Linux software is for mirror presence?
Yes, yes.
Mirror is possible with
Thematic software. You are correct. So basically, Mimic software will work these basic functions, like exporting the DICOM images and then reconstructing that. But for designing these kind of implants, so that is a thematic software. It's same Materialize Belgium. So that software will help to design this kind of customized implants.
Some distinct towards task.
Yeah.
Sir, what would be the lifespan of that specific designs you have done?
Yes, a lifetime. It's a permanent implant.
Yeah.
Normally, we have two kinds of implants, but
Okay.
this is a permanent lifetime implant.
Okay.
But the literature and says like it's, but you have a very good osteo integration. That is a major thing.
So it doesn't have any infections.
No. No, titanium is a FDA
Titanium.
approved and it's a biocompatible. And it's a FDA approved.
that material it's okay.
Even
Only
for
thing the
dental also we
lifespan.
are going to use like that.
Any other the pain, the side
Yes,
effects,
so far,
side
so far
effects?
so good.
For patient,
yeah, literature is
luckily.
saying, and for with our experience.
Luckily,
That
yeah.
is the skill of the person who is
Yeah. And yes, that is also another factor, important factor.
Yes.
among the materials.
These are titanium?
Yes, titanium.
Is that normal for jaw height
Yeah.
implants?
Yeah.
Understand.
Yeah. Titanium 6.4. It's that great.
So among the materials available for this bio-based applications, the titanium is the long-lasting life.
Yes. Yeah. Cobalt chrome is also there, but yeah, cobalt chrome we have other areas.
Cobalt,
But especially this wall maxillofacial, titanium and peak is also. Biopolymer if you are looking at.
Professionals prefer titanium.
Yeah, titanium will have a lot of advantages.
And it's fast.
And then this is like a lattice-based design we have done for lightweighting. For lightweighting of these implants. So and then also integration also. Like once you are fixing this foreign body and it's going to adjacent to your original bone, then it should get married together. Means it can match. Compatibility. And then in order to do such kind of a thing, we are mimicking the design as like a bone, porous design, like a lattice design, lattice structure. Which Uday is working on. So the lattice-based design for improving RCU integration.
Otherwise, the other part of the bone is going to wear.
Correct.
That is the problem.
Yes. So we are mimicking almost like how exactly the original bone, if you look at, it is a outer, it is a harder, and if you go inside, it is a porous. It's a sandwich kind of a structure. So then exactly you are trying to mimic the same patient porosity by designing it. That's magic of design, which we are trying to. And further, the magic of AM only can build such kind of porous structure. Somewhere it is porous and somewhere it is solid. It's combined. It is. So it is a design as well as the magic of AM.
So among SS and titanium, which is preferred for this
Titanium. Medical purpose is titanium. Stainless steel 316 also people are using it, but if you see the oral maxillofacial and other joints, so they are using titanium. But wherever you
for bone and
for the bone 316L, they are
which is cheap.
Yes. Correct. Yeah. We need to do. There is.
If there is a gap, then
Yes. Yeah, that everything should be checked before. Yeah, and then some extent the simulation studies also. The dynamics part of it. Yeah, then FEA and So we can see this is the interface where this machine, this 3D expert, there is a one software. Initially, pre-processing software will be there. So then you take the STL file, and in that, the 3D expert. Yeah, this is a build setup. So we made how many? 35 million. 35. This is the build. So it's exactly the size of the build volume of the machine. So then, which we can see, we can organize all these parts. So right now, 35 parts, cylindrical coupons here. So then we have options here, like in a CAD. Like probably you might have used some Cura other software for DM. So the same thing, like basically what we do, we can import CL files. And then we will slice the object. Yes, that slice data, the laser part will be sent. Correct. Yeah, the laser part data in this software will be sent. Thickness right now we say 30 microns. The height of the curve. Go to height. 80. Height, I need to check. Height of the thing? What is the height of the cylinder?
This is 10 mm. This is 10 mm. But we can go up to 8 mm. This is 10 mm.
10 mm. This is 10 mm. So you can go up to 80 mm. As I said, the 100 by 100 by 80. 80 is the Z maximum height. Correct. There are number of ways. So and basically we have to supply argon gas. Inert gas is argon, which we need to form, and that inert gas, either we have two options. One is argon. Argon goes with titanium, and then nitrogen goes with the steel. The reactive materials and non-reactive, because argon again a bit expensive than compared to nitrogen. And nitrogen will go with the steel, cobalt, chrome, and aluminum and titanium. The argon has to higher end applications. Argon gas has to. And we have a compressor also. Yeah. So if you pumping, correct. Yeah, for pumping. We have two options. I say like nitrogen and argon. The proper composition. So then we need to maintain a ppm and this gas will come here inside.
Inside the
temperature. Normally, yeah, we have an option of preheating a powder also, which we have a oven there. Yeah, we'll be drying it and also little bit of preheating. Yeah, it will reduce the energy, the laser. So the powder will be shifted here where we have there's a oven, like we'll put it in the oven, and then we have will be loaded. Yeah. And you might have seen the piston and there is a roller. If I spread the same powder bed base.
what materials in the powder bed, what materials?
Yeah, that's what we have. Right now we write 4 materials. One is cobalt chrome, aluminum, titanium, steel, 17.4 pH. Steel.
Whatever resolution.
Smallest resolution, yeah, it will even maybe 3 micron, 4 micron.
If I want to make cylinder like a pin,
I understood. What is the minimum wall thickness?
Diameter pin,
Or minimum diameter of the pin you are talking about.
If I want to.
Typically you can go maybe 1 mm, less than 1 mm also. 0.5 mm.
Takes lot of risk.
Yeah, 0.5 mm also it will realize. So again depends on the laser part diameter, but that is.
But it is possible. Up to
Yes, we can. 0.5 mm you can. Maybe it's a laser, na, but FDM you cannot. It's a laser part size is very small. 0.5 mm we can laser. So basically, as we know that this powder and the full melting technique. So no post processing. Normally, if you go with the partial melting, somebody was asking there, yeah, then centering should be furnace treatment. But here, you will get a 100% dense part out of the machines. But still, in order to relieve residual stresses, we have a furnace.
So residual stress again, if the size is large,
Yeah.
it doesn't matter. If it is a plate, I would agree that warping and
Yeah, again depends on the geometry and the shape of the part where your residual stress will vary. So if you have more surface area, obviously we'll have a more warpage. Yeah.
like imagine the mold and bulky mold.
Bulky, yeah.
Then I think whether it matters.
If you have a bulky material, always there will be chance warpage.
So
But in that case, you do put it in some inclination. So if your mold is flat mold, and if you are keeping like this, so you have a huge residual stress. But you make it 10 degree or 20 degrees. So at a time, your layer, say for example, if you are keeping like this, so at a time you have a huge mass here. But same, if you put it some 15 degree or 20 degrees, so a single layer is subjected to only less contact area, means that less residual stress. But always don't use this orientation. You put it some in order to minimize that residual stresses and warpage. Give some inclination, but we need to give some support. That way we can. So once you complete this part,